Welcome back, everybody. This is our fourth class in JEE Mains previous year questions for chapter Moving Charges and Magnetism of class 12th. Before this, in this series, we have made three videos, and all of those videos are available on our YouTube channels. And we have also started similar series for NEET previous year questions. So you can go to our channel and in playlist section can also find those videos out. And if you find these videos useful, then do press the like button, share them as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. With your donations, we will be able to keep on making these videos on regular basis. So with this, let's start today's video. And in the previous one, I think we covered up to question number 25 or something. Yes, this was the last question which we covered, and today we will go with the next one. So here we have a charged particle with charge q enters in a region of a constant, uniform, and mutually perpendicular orthogonal fields E and B with velocity perpendicular to both of them and comes out without any change in magnitude or direction. Then, so here charge particle is moving in mutually perpendicular electric and magnetic field. Velocity is perpendicular to both electric and magnetic, and same for the electric field, that it is perpendicular to both velocity and magnetic field, and same for the magnetic field also. So here we have to find out the relation between uh, velocity, electric and magnetic field in the in form of vector. In normal scalar form, we know that velocity is equal to E magnitude of E divided by magnitude of E. That's the scalar form which we know. Now we have to derive a relation for a vector form. Now we know that electric force is Q times E and magnetic force is Q times V cross B. And when particle is undeflected, it comes out without any change in magnitude, then it means that both of the forces, the vector sum of both of these forces is zero. As a whole, there is zero force or net force acting on the particle is zero. So we can say their vector sum will be Q times E plus Q V cross B is equal to 0. From this we can write that E plus V cross B is equal to 0, and from this we can write that E is equal to negative of V cross B, or we can write that E is equal to B cross V. So this is the basic relation which we can form using these two. But as we can see in the options, we have to find out relation for the velocity, not for the electric field. And in all of these, what we are getting, in some options we have E cross B, and in some options we have B cross E. So what we are doing, what we will do here, we will take cross product of both of the side with B. So we will be using cross product of both sides will be B with B. So it comes out to be E cross B, cross product of the left hand side with magnetic field and cross product of right hand side with the magnetic field. So B cross V cross B. So we will do this. Now for this we have identity, and identity says that if we have A cross B cross C, these are three vectors, and using identity we can say this will be A dot C. Here cross product is removed. We can say C comes in and B goes out. So A dot B into A dot C into vector B. B stay in the vector form. They all are in vector form. Minus we have Now again C comes in. Now in the first phase B was out. In the next phase A is out. So we will have A vector into B dot C. So this will be the answer of, we can say this is the identity we are going to use here. So E cross B will be, first V is out, so we will have B dot B into V minus, then we have this B will be out and we will have V cross V dot B. Now, as we already know that velocity is perpendicular to both electric field and magnetic field. Means the angle between them theta is 90 degree. And in case of dot product, if angle is 90 degree, that term reduces to 0. And here B dot B will be magnitude B square. So we will have E cross B is equal to B square into V vector, and this whole term will reduce to 0. And finally value of velocity in vector form will be E cross B divided by B square. So E cross B divided by B square, that is the right answer here. So option B will be the right answer. Moving to the next one. A charged particles move through a magnetic field perpendicular to its direction. Then kinetic energy changes, momentum is constant. Momentum changes, kinetic energy constant. Both does not change, and both constant. So we know that formula for momentum is mass into velocity, and formula for kinetic energy is half mv square. Now, when magnetic fields apply some force on a moving charge particle, then that force, magnetic force, uh, acting on a charge particle is perpendicular to its velocity. So, what does it mean? That magnitude of velocity does not change, but direction keeps on changing. So, if direction is changing, then velocity can go from positive to negative. As direction is changing, so velocity can take positive to negative sign, means momentum will change. But as from the formula of kinetic energy, we know that here we have v square. So even if velocity becomes negative, the square term will reduce the effect of negative term. So in short, as we have square terms in the kinetic energy, so change in direction does not matter in kinetic energy. So it will stay constant, kinetic energy will stay constant, as magnitude is constant for velocity in case when magnetic force is acting on it. But as magnitude is constant but direction is changing, so momentum can take either positive or negative values. So that's why momentum will change. So momentum changes, but kinetic energy is constant. Option B will be the right answer. In a region of steady and uniform electric and magnetic field are present, two fields are parallel to each other. The charged particle is released from the rest in a region. The path of the charged particle will be. So we have to find out path of the charged particle. Now suppose these are our coordinate axes. And we have electric and magnetic field acting both in the same direction, that is x-axis. We have electric field here and we have a magnetic field here. So suppose this is E vector and this is B vector. And charge particle is at rest. Initially charge particle is in rest. Suppose we release a charge particle here. and assuming that this is a positive charge particle. This charge particle has a positive charge. Now what will happen? Now as electric field is acting in the x direction, so there will be a force acting parallel to the direction of electric field on the charge particle. So charge particle will start moving in the x direction. And as we know now, charge particle have some velocity, and that velocity is in x direction, and magnetic field is also in the x direction. So we can say that magnetic force will be q v cross b, and as v and b both are in same direction, so their cross product will be 0. Hence what will happen, there will be no magnetic force acting on the charge particle, so charge particle will keep on moving in a straight line. So option b will be right answer. Moving to the next one. A charge particle of mass m and charge q travels on a circular path of radius r that is perpendicular to magnetic field B. Time taken by particle to complete one revolution. So its initial velocity, suppose let's take v, then radius of the charge particle, we know that radius is given by mv by qb, and from this we can find out that velocity will be r q b by m. Now it is asked to find out the time period to complete one revolution. Now, in one revolution, it will travel path equal to circumference of the circle, that is 2 pi r, and this is the distance divided by velocity give us the value of time. So from this formula we can find out r by v. R by v will be equal to m by qb. So it will be 2 pi into m by qb, which is option C. Moving to the next one. Uniform electric field and uniform magnetic field are acting along the same direction in a certain region. If electron is projected along the direction of the fields with certain velocity, then here we have again electric and magnetic field are in same direction. Suppose this is our coordinate axis. So electric field is in same direction and magnetic field also in same direction. Now electron projected along the direction of the field with certain velocity. So it is projected with certain velocity parallel to the direction of the fields. Now what will happen? Again, as it is electron, so now first coming to the electric force, the force acting on it will be in the opposite side. So the electric force acting on this electron will be in the negative x-axis. And coming to the magnetic force, as magnetic force is q v cross b, and as angle between the velocity and the magnetic field here is 0. Initially it is 0, so there will be no magnetic force acting on the charge particle. So what will happen? So we can ignore the effect of magnetic field, only electric field's effect will be there. And as force due to electric field is acting in the reverse or in the opposite direction, so electron will feel here a deceleration or negative acceleration. So slowly its velocity will decrease, and then after it will start moving in the opposite direction. So assuming initially it was moving in the right direction, then it will start moving in the left direction. So now as we see the analyze the options, we have two possible answers. That first, its velocity will decrease, and second, it will turn towards left of direction of motion. Now we in the question statement, actually it is not defined that initially it was moving in which direction. initially either it was moving in the right direction or it was moving in the left direction. So it is not defined. So we cannot say we cannot say with surety that it was moving in the right and now it is moving in the left. Reverse is also possible, that initially it was in left and now it is moving in the right. So we can be only sure about the answer, that option B, that its velocity surely will decrease and will turn to negative. Now moving to the next one. Particle of mass m and charge q moving with velocity v describe a circular path of radius r when subjected to uniform transverse magnetic field of induction B. The work done by the field when the particle completes full circle. Now we have to find out work done by which field? We have to find out work done by the magnetic field. And we know that power is force times velocity and power is work upon time. So F dot V. So from this work we can find out that it will be F dot V into time. And as when we write it for magnetic field, so FB dot V. And we know that magnetic force act perpendicular to velocity, so their dot product is zero. So work done by magnetic force is always zero. So that's why it only changes the direction and not the value or magnitude of the velocity. Now moving to the next one. If an electron and proton having same momentum enter perpendicular to magnetic field, so I think we have to compare their radiuses, and it is mentioned that they have same momentum. Now R, or radius, when a particle enters into magnetic field, is given by mv by qb, and we can write mv as momentum divided by qb. So from this we know that electron and moment and protons momentum is same, so p is same for both of these. Magnetic field will stay constant, and regarding charge, both of them will have the same charge in magnitude, just signs are different. So what will happen, that their radius will be same, but rotation will be different. And how it will be different, let me explain. Suppose this is the region of magnetic field. This is the region where we have magnetic field. Now suppose there is an electron. An electron enters here. So electron might take this path. If electron is taking this path, then proton will take opposite path like this, and vice versa. If proton is taking we can say anti-clockwise, then electron will take clockwise path. So their sense of rotation will be opposite, but their radiuses, these radius will be same. So option A will be the right answer. Moving to the next one. The time period of a charged particle undergoing a circular motion in a uniform magnetic field is independent of its speed, charge, mass, and magnetic induction. So we just solved value of time period in the some, I think, previous question, one of previous question. Here it is. Time period is 2 pi m by qb. So time period is 2 pi m by qb, and from this we can see time period depends upon mass, magnetic field, and charge. So we have only one option left, that is speed. That time period does not depend upon the speed of the particle, it stays constant. So option A will be the right answer here. Moving to the next one. A charged particle going around in a circle can be considered as a current loop. A particle of mass m carrying charge q moving in a plane with v, with velocity v, speed v, under the influence of magnetic field, the magnetic moment of the charged particle is. So we have to find out magnetic moment, and here we can use that relation. Here we can use we can say the ratio we have, also known as gyromagnetic ratio. Let me slide it first. It is known as gyromagnetic ratio, and it is a ratio of magnetic dipole moment by angular momentum, and it is always constant and is equal to charge of the particle divided by twice of its mass. So mu is here magnetic moment or magnetic dipole moment, which we have to calculate. L is the angular momentum of that particle, Q is the charge, and m is the mass. Now charge particle is moving in a circular path. So suppose this is the center and charge particle is moving like center in circular path. So its angular momentum will be its linear momentum times r. So mvr. So mu by mvr is equal to q by 2m. M get cancelled and value of mu comes out to be q vr by 2. Now we can't see any option such like that. So what we do, as particle is rotating in the magnetic field, so it will have some radius, and the radius is given by mv by qb. So putting that value of radius here, so qv by 2 into mv by qb, q get cancelled and we have mv square by 2b. Still none of the option matches, but we can see here that we have b by b square. Everywhere we have b by b square. So what we do, we multiply it by b and multiply it by b. So we will have mv square p divided by twice of b square, and with this we have option A and option D our possible answer. Now regarding taking positive and negative sign, that will be decided by the sense of the rotation, and it is not mentioned here. So both option A and option D both are possible here. Normally most of the cases we take positive options, so that's why we will go with option A. Moving to the next one. Here we have wire A bent into the shape of an arc of a circle carrying a current of 2 ampere having radius 2 centimeter. Another wire B, so initially we have this wire, another wire B also bent in the shape of arc of a circle carrying a current of 3 ampere having radius 4 centimeter, are placed as shown in the figure. The ratio of magnetic field due to the wires A and B at the common center O. So we have to find out magnetic field ratio at common center O. And as we can see, let's go for the first wire A. The wire A's arc is making what we can say, it has 90-degree part missing out of it. The wire A looks like something like this. This is center O, and it has a circular shape, something like this. And this angle is 90-degree as mentioned. And it has a, we can say, out of whole circle, we have 90-degree path missing. So in this case, magnetic field at the center will be given by mu naught I by 2r into theta by 2 pi. And what is this theta? This is the angle which is actually inscribed, as in this case out of 2 pi only pi by 2 is missing. So here in this case theta will be 2 pi minus pi by 2, or it will be 3 pi by 2. And in the second case we can say that is B1, and B2 will be given by mu node, that is I1 R1, and theta 1 also mu node I2 by twice of R2 into theta 2 by 2 pi, and theta 2 will be is equal to 2 pi minus, because in the second loop only 60 degree is missing, and 60 degree is equal to pi by 3 radian. So pi by 3, so it will be 5 pi by 3. So their ratio, we have to find out ratio. So ratio will be mu node and 2 are same for both, and 2 pi is same for both, so they will get cancelled. We will have I1 by I2 and R1 by R2, and also theta 1 by theta 2. So putting these values, I1 is 2 ampere and I2 is 3 ampere, so 2 by 3. Radius 2 centimeter, 4 centimeter, so 2 centimeter, 4 centimeter, and we are not changing units here because both centimeters will get cancelled to each other. And theta 1 is 3 pi by 2, 3 pi by 2, and theta 2 is 5 pi by 3. So here pi get cancelled and 2 get cancelled. We will be left with 4 into 3. This 3 will go on the top, divided by 3 into 2 into 5. So 3 get cancelled and 4 get cancelled at 2. So this will be 6 by 5, or 6 ratio 5 will be the right answer. Moving to the next one. Magnitude of the magnetic field at the center of a hexagonal shaped coil 10 centimeter, side is 10 centimeter, 50 turns, and carrying current I in units of mu node by I. So we know that if we have been asked here electric field, then value should have been 0. But magnetic field is not 0, and let us draw a hexagon here. I think, yes, here it is. Suppose this is our hexagon with each side 10 centimeters. So A to B, that distance is 10 centimeter. Now we directly don't have any direct formula for hexagon, but what we can do, we can use here a formula for a magnetic field due to a straight carrying conductor. Suppose straight conductor. Suppose we have a conductor here, and we have a point here. Suppose point, we can say point X, and this is the center for this. And let me draw all another. And this is the for angle for the one end, and this is the angle for the other end. Assuming this angle is theta 1, this angle is theta 1, and this angle is theta 2, and there is current I flowing through this parallel conductor. So then magnetic field due to this conductor at this point X is given by mu node I divided by 4 pi. The distance, that distance is d, 4 pi d, into sine of theta 1 plus sine of theta 2. This is the value for formula for the magnetic field. Now we will do same here. As this has a center and this side is 10 centimeter, we know if we join these two lines, if we join center and these two, suppose center is at O And we can form similarly six structures like this. Let me draw also. 2, 3, 4, 5. Assuming all angles are theta, so all angles must be equal because it is a hexagon. So the value of all these angles will be, supposing this angle is equal to theta, this angle is equal to theta, then theta will be equal to 360 by 6 because there will be 6 such angles, or theta comes out to be 60 degrees. Now considering ABO, consider here AB as a parallel conductor like this one, and O as the point at which we have to find the magnetic field. Now if we divide in the two parts, if we divide it into two parts like this, then this angle will be half of theta, or 30 degree, and this angle again will be half of theta, 30 degree. 30 plus 30 is equal to 60. So our conditions are met. Now due to this conductor, due to this 10 centimeter conductor, and let's also find the distance. Suppose this is point D. So in triangle AOD, in triangle AD, we know that this length is equal to 5 centimeter, and this angle is theta. So we can say perpendicular upon base, or perpendicular is AD, base is OD, is equal to tangent of 30. AD is 5 by OD, tangent 30 is 1 by root 3. So from this OD, or base, comes out to be 5 root 3. So our distance is 5 root 3. Now magnetic field due to this conductor AB at the center O will comes out to be, so magnetic field will come out B due to AB, it will be mu naught times I by 4 pi into distance, that is 5 root 3, into sine of 30 plus sine of 30. Sine 30 is half, and into half plus half, that is 1. Now putting all the other values, as our answer is in the form of mu naught I by pi, we have to calculate our answer in mu naught I by pi. So we will we will not put a value for mu naught I and pi. We will keep them as it is. We will have 1 by 20 root 3. This is the magnetic field due to only AB part. Now we have like 6 parts available here, or 6 conductors available here, like AB, C and C. We have to like BX, Y, Z, O. So we have similar 6 conductors available here, like AB. We have BX, we have XY, we have XZ, we have XM, and we have MN. And we can easily find out using right hand rule that if current is flowing in a clockwise direction, assuming current is flowing in a clockwise direction, then direction of magnetic field due to all of these conductors at center will be going inward into the going inward into this screen's plane, or going into negative k direction, negative z direction. And if direction of current is anti-clock, then it will be coming out of the screen. So magnetic field of all of these will add up at the center, or we can say B, total B will be 6 times of this. So mu naught I by pi into 620 root 3. So this will be the magnetic field due to one loop. And we have here such a 50 loops, 50 turns we have such there. So it will become mu naught I by pi into 50 into 6 divided by 20 root 3. And I think the option answer should be in terms of meters, because here we have length in centimeters. So this OD is should be into 10 raised to power minus 2 meters. So here we have 10 raised to power minus 2 with minus 2, and here minus 2. So it will become 3, or we can say 15 mu node I by pi, 15 into 100, 1500 by root 3. And we can further simplify it by multiplying with the root 3 and dividing by root 3. So root 3 into root 3, 3, and 1500 divided by 3 is 500. So it will be mu node I by pi into 500 into root 3. So this will be the answer in terms of units of mu node I by pi, and that is our option C. So option C will be the right answer here. Now moving to the next one. A long straight wire of radius A carries a current distributed uniformly over its cross section. The ratio of magnetic field due to wire at distance A by 3 and 2A respectively from axis of the wire. So suppose this is our wire's cross section. This is the cross section of the wire, and this is wire. This is the center of the wire, and it carries, we can say, it carries current distributed uniformly over its cross section. So suppose it is carrying current I. Current is equal to I, and we have to find out magnetic field at distance A by 3, where A is the radius of the wire. Now, as we know that this distance is A, and we have to find out magnetic field at distance A by 3. So suppose at some this point means we have to find magnetic field inside the wire. And for that, what we will do? We form a closed loop, and we'll apply the Gaussian law for magnetics. We can say B dot ds integral is equal to mu node I. So B is the magnetic field at any point on this circle A, and ds is its circumference. You have to remember that here ds is the circumference. If I write same formula for electric field, in that is area. So we can say we will number as b1, because I think we have to find out ratio. So b1 into 2 pi r, that is a by 3, to find the circumference, mu node times I, that how much current will be enclosed in this circular area. So as I current is distributed uniformly over the whole cross section, so we can say current will be I divided by pi a square into pi a by 3 square. As current I is distributed uniformly over whole cross section, so it is distributed over pi a square area. So current per unit area is I, yes, current per unit area is pi a square. And when we considering a circle of radius a by 3, then its area is pi into a by 3 whole square. So current in this area will be I pi a square into pi a by 3 whole square. So now solving this, b1 2 pi a by 3 is equal to pi get cancelled, and we are left with mu node I. A square will also get cancelled, and we will be left with 1 by 9. So 3, and formula for p1 comes out to be mu node I divided by 6 pi a. That is for b1. Now considering b2, that at distance 2a. Now our circle is at distance 2a, means outside of the wire. Now let's slide it slightly. Now when point is outside of the wire, we can again write that integral b2 dot ds is equal to mu naught I. Now b2 will stay as it is. Now circumference will become 2 pi into radius, that is 2a, is equal to mu naught times I, because when we have crossed the wire, the amount of current will not change. Inside the wire, current was distributed uniformly, so that's why value of current was changing. But as we are outside of the wire, then the current is uh, in this portion. When we are outside of wire, there is no current, so the only current that is due to wire, and as whole wire is inside this circle, so current will stay. The maximum value of current is available to us, that is flowing through the wire, and that is I. So from this, b2 comes out to be mu naught I by 4 pi a. Now we can divide both of these. So b1 by b2 will be mu naught pi get cancelled in both, pi a cancelled in both, so 1 by 6 into 1 by 4, and the ratio is 2:3. So let's find that which one. So the ratio at a by 3 to 2 by a, it will be 2 by 3. So option A will be the right answer here. So with this, we end this video here. Hopefully what we have covered here till now is helpful to you and understandable to you also. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to answer those all. And if you like these videos, then do press the like button, share them as much as possible, and subscribe to our channel. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want, however amount small, or whatever the amount you donate will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.